Hi, this is Jeff Blair, Schneider Electric. I'm also ISA senior member assigned to the St. Louis section. Today I'll take a few minutes to talk to you about radar for solids and powders. This is a topic that I get questioned about quite a bit. Forgive my crude artwork here. When we look at some of the instrumentation we've used for solids and powders in the past, I have to tell you there's nothing wrong with any of these types of methods, nothing at all. It just seems that in today's market, radar gains more and more popularity because it's simple and easy to use. These would be level switches that either they stick in the side of the tank and either tell us if they see level or not, on or off. So you can see this one would be triggering level. This one hasn't seen anything yet. Ultrasonic level measurements using sound waves, acoustic waves, non-contact to sense the level. And then we have mechanical methods such as plumb bobs or ropes, where a person physically gets on top of the tank and drops a rope through the top of the tank to check the level. When you look at the drawing, you have to consider that solid applications are often jagged and rough. There usually are no smooth surfaces in a solids level application. You've got angles of repose, you've got rat holes, you've got material filling, emptying. It's a difficult application. And on top of that, solid applications often have very low dielectric constants. They might have dust in the atmosphere. They're not easy applications to measure. When you look at radar, though, radars are growing in popularity for solids level applications. This is our lineup. This is the LR65, which is an 80 gigahertz frequency. The LR64 is a 24 gigahertz frequency. And the LG01 is a guided wave radar. Our presentation today will talk about these two. And again, remember, there is no perfect radar for every application. The LR65 is the overall it's the most universal of the two radars. Why is that? It has an 80 gigahertz frequency, and that 80 gigahertz frequency has a small wavelength that can measure any size medium. The smaller wavelength is conducive to small particles like fine powders, but it can handle the bigger stuff too. It provides an increased focus. This narrow beam gives an increased focus, which leads to better dynamic range, better reflection off the material, a good ability to work with dust, and because of that narrow beam, you could even place it in a high nozzle. The LR64 is a 24 gigahertz radar, and a 3-inch drop antenna, which is this kind of circular antenna here, produces a 9-degree beam versus a 2 3/4-inch lens antenna has a 4-degree beam on the LR65. So you get a little bit wider beam, and at 24 gigahertz we've got a larger wavelength. The LR64 is more applicable to particle dimensions that are bigger, like rocks and granulates. If you use the 24 gigahertz, you can pick between a drop antenna and a horn antenna. The drop is the perfect choice for bulk solid applications in dirty environments. And why is that? It's because adherences of bulk solid material like condensed water are largely avoided by the smooth surface of the antenna. Also, adherences are generally less critical with the volumetric plastic body of the antenna. Taking a closer look at the drop antenna for the 24 gigahertz, it's no purging required for this. Actually, purging is not available, and that can save some time and money when it comes to putting in a purging system. But because of that round antenna that generally resists buildup, you're not going to need any type of purging. Now, by contrast, this is the only antenna available on the LR65, the 80 gigahertz antenna. It's called a lens antenna. There's no protrusion into the tank. It's made of PEEK material, and as you can kind of see in the drawings here, it doesn't protrude out hardly at all. So now that you've had a chance to look at both radars, you might wonder which one you like best or which one we would recommend. 80 gigahertz is the more universal. As I said before, it can handle the small stuff and the big stuff. But the main reason it's more reliable is it has a smaller beam size, and that smaller beam gives a better reflection off of those challenging solid surfaces. You've got rough edges, you've got rat holes, you've got angles of repose, you've got low dielectric constant materials. You're going to get a much more reliable signal, more signal down, more signal back from an 80 gigahertz radar. If you need evidence as to what's going on in other industries, take a look at the auto industry. Automotive radar are moving from 24 gigahertz to 77 and 80 gigahertz on new cars. And it's the evolution of technology. They're more accurate, they have higher resolution, and just like we've seen other advances in the auto industry, fuel injection, unleaded gasoline, the radars are becoming the same. And think of what the radar in your car is measuring. We talk about liquids as an application. It's not like you've got a pool of water in front of your car that the radar is trying to get a reflection off of. It's actually measuring solids. You've got a plastic bumper or a metal bumper off of a car in front of you. So those are challenging applications as well. And an 80 gigahertz radar in a car, which is often behind the front emblem on your front grille, they really do a fantastic job helping us drive. So we've talked about the challenges that solids level radars face. What are we going to need to do to ensure we're giving the radar the best chance at success? These are some of the accessories you may want to purchase or use with your solid radar. We want to make sure we're going to install the radar properly. Let me explain briefly why you may need these accessories, and then I'll show you where you can find them. But first, I have to go back to our LR65 example. In a solids level application, a rule of thumb is that whatever the radar beam sees is averaged out by the radar processing algorithms and software. We know there are almost no even surfaces in solids level measurement. If your client would like to average somewhere outside the normal beam angle, you can do that for them. The photos on the left and middle illustrate a radar that's flat. It's sitting, nicely on top of a nozzle here. And this one is angled, as you can see. So why would you leave the radar flat, or why would you aim it? You have to think about, where do you want the beam to hit? If we install our radar on the top here and it shoots straight down, let's assume this red dot is where the beam intersects from an 80 gigahertz and the yellow is from a 24 gigahertz. That may be fine for you and your client. If they want to know the level or the distance right there, certainly we can do that. If they want to know it more here in the middle at this angle of repose, you would have to aim the radar there. And if you look at the difference between the red circle and the yellow oval, this is the difference between 24 and 80 gigahertz. Assume the yellow, the bigger wave, is the 24 gigahertz. This is the advantage the 24 gigahertz had. We talked about how the radar averages what it sees in the solids level application. It's taking samples from all the points it sees in the wave. This is the advantage a 24 gigahertz has, because it's got a little bit wider angle. It's going to actually see more of that solids level and be able to give a better average of what it sees. The drawback is you might not get as much reflectivity, you might not have as reliable of a signal, but you do get a nice average. So just keep in mind, are we going to try and intersect the level here? Are we going to try and do it here? It all depends on what you and your client need. If you do decide you want to tilt the radar so you can aim the beam, here's a couple of accessories you might want to look at. This one's called the orientation system. It can angle the radar up to 30 degrees. Here's another look at the orientation system. And then this is a 2-degree flange, just to give it a little bit of a tilt. To specify or purchase these, you can go into this link, and this will take you to a page on the Schneider Electric website where you'll find all this information. Just enter this part number in by automation. This is the 2-degree slanted flange. And this is the 30-degree orientation system. It allows a little more flexibility in terms of aiming a radar beam. When it comes to aiming, remember, you don't have to aim it. It depends on where you want to see that beam intersect the level. And if you want to do something outside of that, you can actually install 2 radars if you want to try and get a profile of your solids or powder level application. We hear so much about dust, and yes, the radars can work with dust. You might probably have dust in a solids application. To remove the potential for very thick dust that can disrupt the measurement, we use high-pass filters to remove errant dust signals close to the antenna. If you've got experience with radar, maybe you've seen this before, this is an air purge option. I'll read verbatim from the instructions what we say in regards to using a purge to keep things clean. If it is necessary to clean the lens antenna, you can attach a purging system adapter to the device. This part is available as an accessory for devices with threaded connections. Here's the purging system right there. You hook up your air here. Here it is for the LR64. If it is possible that there will be buildup or condensation, purging options are available for metallic horn antennas. Purge the antenna at intervals to make sure that the inner surface of the antenna stays clean and the device measures accurately. Remember, we talked about the drop antenna. There is no purge available for the drop. Before I depart, I want to go back to the algorithms. If you've watched this video, maybe you're thinking, okay, what's the difference between a liquids radar and a solids radar? For example, how are the 80 gigahertz LR75, which is a model for liquids, and the 80 gigahertz LR65 different? They're both 80 gigahertz. They both measure level, and besides some differences in available antenna sizes, they're very similar, except how they process signals and their algorithms. Each radar has specific algorithms that make it specific to use in liquids or solids. When we're working with liquids, usually only a single measurement is enough to get a good, reliable measurement. Liquids have a highly reflective surface. That's not the case for solids because the reflections are weaker and can be mixed up with erratic signals. What we do is we overlap several measurements to determine which signal is the true level. Remember, we talked about that averaging of what the beam sees. Finally, I'd be remiss if I didn't mention how solids are normally measured. It may be level or distance, but it's often volume or mass. You can build a strapping table with a minimum of 2 entries in the display or by using packware to calculate volume or mass inside your vessel. I sincerely appreciate your time. I hope you found this video to be beneficial. I just want to leave you with this parting shot showing some of the pros of each of the models. Overall, the LR65, the 80 gigahertz, a focused, more reliable signal. And the LR64, the 24 gigahertz, it's got a wider beam angle for a good average. Thank you for your time and attention. I really appreciate it.